And you can pass this one out, which is a plot on hydrogen. We'll get to it in just a little bit. But we have to come up with some definitions of different terms that are similar in metallurgy. There is, actually let's do hardness first. I talked about hardness yesterday. You use a little indenter, and this is the definition out of the ASTM Materials Engineering Dictionary. And it says hardness is a measure of the resistance of a material to surface indentation or abrasion, may be thought of as a function of the stress required. It turns out some of the tests are actually 1/3 or 3 times the tensile strength. And if you take my deformation processing, you can prove it mathematically that it, in a non-plastic, non-work hardening material, it should be exactly 2.57 times, but because it work hardens, it's about 3. And we talk about what happened to this thing. I put a new battery in it and it was working this morning. Oh well. So we talk about Brunel, Rockwell, Vickers, Knoops types of hardness tests. So hardness is just a measure of the strength of the material in its heat-treated or non-heat treated condition, whatever condition it's in. Now, hardenability, on the other hand, is the relative ability of a iron alloy to form martensite. Martensite is this non-cubic crystal structure that is very hard when quenched from a temperature above the critical temperature. And you can get hardnesses above 50 Rockwell C, which is sort of like this metal file is probably 55 or 60 on the ends. Okay, so hardenability is a function I showed you of the carbon content and also the alloy content of the material. Hardening is, you can increase the hardness of a material by various heat treatments, age hardening, which we do with aluminum, flame hardening, induction hardening, precipitation hardening, quench hardening. Steels are quench hardened so far as that goes. So there's lots of ways metallurgists have to try to change the strength of a material. Hardness is a measure of the strength, whereas hardenability is actually a measure of the depth. So we look at it like this. Hardness in steels is a function of the carbon content. And I showed you that before. In low carbon steels, you can't get more than Rockwell C 20 or 30, but if you increase the carbon up to about 0.6% carbon, you can get Rockwell C 60, and the curve bends over. I guess I could find the curve somewhere here. Hardenability, on the other hand, is a function of the thickness of the steel and the alloy content. What other elements? Chrome, nickel, molybdenum, and whatnot. And if I look at just a plain carbon steel, this is a 1021 steel, and I look at, that irritates me. Had it working last night. Anyway, this is the distance from the quenched end of a bar. So they just take a cylindrical bar, put a shield around it, and they quench the hot steel just by hitting it with a strong jet of water at one end, and they measure the hardness into the steel in 1/8 of an inch units. So you can harden a 1021 steel, which is a low carbon steel, easily weldable, a little bit higher carbon than you make an automobile sheet metal out of, but you can only form martensite to about 1/8 of an inch, or 2/8 of an inch, 1/4 of an inch deep, maximum, because the reaction is so fast. And I'll show you what the reactions are in a little bit. Actually, maybe I'll show it to you now. I'll show it to you later because I can't find it right now. Okay. Well, the problem is I want to make something that's strong, like, that's 2 inches, 4 inches, 6 inches thick, so I can make a plate that's strong and has high strength. Okay, so this is the maximum I could get with a 1020 steel was about 40 Rockwell C. I could get 60 Rockwell C if I had a higher carbon, that's hardness, but I can't get much deeper with high hardness. So what do? I have to add an alloy, and the alloys I add, let me dig this out, might as well do it. Where did it go? Sorry about that. Okay, here it is. Okay. So we have curves, and there are whole books with these types of curves, which are called continuous cooling transformation diagrams. So if I heat a steel up to, this would be Fahrenheit, 1400 degrees Fahrenheit, or actually I heat it up to about 1600 or 1700, and I quench it in water. This is time on a log scale, so this is 1 second. I have to quench that and cool it down within less than a second. This is for 8630 steel. I have to cool it down within less than a second to get 100% martensite. Okay, I might not transform all the austenite, which is the phase at high temperatures, but if I want to get my martensite, I've got to cool it down in less than a second. If I add alloying content to this, I can push what we call the nose of this curve all the way over. So this is the transformation curve. If I cool at a slow rate like D here from a higher temperature, I'll go through the transformation to ferrite. If I have something in this region, I can transform to bainite, which is this sort of region that the old people before the 20th century didn't know about. Edgar Bain discovered bainite when he was doing tests where you quench into liquid lead and hold it at temperature. So he was able to come down, transform. And we actually do those types of heat treatments now when money's not an object. Okay. It's expensive to do that, but we can do it. So you can take these steels and you can add alloying content. Let me come down here. So here's my rapid quenching to get martensite. Here's my quenching partway. It's called austempering to get bainite. You come down at some intermediate temperature like 600 or 700 degrees, hold it there, and then you cool down the rest of the way. If you cool down slowly through this region, you get ferrite, which is a nice soft steel, easily formed. If I now look, this is a 1080 steel. So this is something that you have to cool down in less than a second. But if I add some alloy content, this is 5140, which is an alloy steel, I can change the shape of that nose. Now I have about 2 seconds. You can say big deal. If I go to 1034 steel, I can't even beat that nose in a second. If I go to a heavily alloyed steel, I can get up to 10 seconds that I can cool it down. Yes?
I'm looking at these 4 numbers that keep coming in front of these different types of steels.
Oh, these are American Iron and Steel Institute designations. The 1000 series are the carbon steels. The 1400 series are the 1000 series are the carbon steels. I can't remember what 2000. The 4000 series are basically a nickel chrome steel. Okay, the 5000 series I think is just a chrome steel, where you've added different alloying elements. The 8000 series is a nickel steel, as I remember, but different. It tells you the family of alloy content. The last 2 numbers, the 34 means it's got 0.34 carbon. The 0.4 means it's 40 means it's got 0.4 carbon. So the last 2 numbers are the hundredths of a percent carbon, and the first 2 numbers basically tell you whether it's alloyed or not. So a 1080 steel, carbon steel, 0.8% carbon. Okay, 5140 alloy steel. I got to go look it up. I don't remember. There are hundreds and hundreds, if not, well, there are really thousands of steels. But you control the carbon content, which are the last 2 numbers, and they've given you various ones here, 0.61 carbon, and the 2 and the 1, the second number will also tell you where in the series you are, whether you're high nickel or high chrome or whatever. HY80 doesn't have an AISI number. The US Navy developed HY80, so it has an HY number. It does have an ASTM spec because the American Society for Testing and Materials is an organization that writes specifications so that buyers and sellers can agree on, you know, what variations in thickness are going to be acceptable. What are the limits of acceptability? What variations in composition? And if you have a fight, you know, how do you referee the fight? How do you analyze the steel composition? What do you get for various types of limits? And some of the specifications have extra things you call out when you order it. So you may order an A106 steel pipe, which is just a seamless carbon steel pipe, okay? That's ASTM A106. But you can say, okay, if you're going to buy that pipe in a 4-inch diameter and you're going to put it in some refinery somewhere, the inspection should be a hydro test where you basically, at the mill, they pump it up with water to so many thousands of PSI. It might take 6,000 PSI to actually burst it, but you pump it up to 2,000 or 2,200, whatever is on the purchase order requirements, and it means it passed. It was a proof test. And if you're going to put this in a critical service, you test every pipe. Now they might be 40-foot lengths of pipe, and then you're going to cut them up. That doesn't really matter. But then, if you don't want it hydro tested, it has to be stamped on it that it's NHT, not hydro tested. Okay? If for some reason you don't want to hydro test, the ASTM spec says you can do other non-electric electric tests other than hydro, which would be magnetic particle, eddy current, ultrasonic. They call that electric tests. They're non-destructive tests. The specifications for the non-destructive test, you can't have a defect greater than 12.5% of the wall thickness. Well, is that the nominal wall thickness or is that the actual wall thickness? Because what you actually buy is going to be a little heavier than the nominal because the nominal is a minimum. Okay? You design to the minimum. Okay? Which is right there in a table in that spec. So ASTM writes these things up. There's an ASTM spec on HY80. I actually tried to look it up yesterday, but there's no way to index the ASTM to HY80 because they would just say it's a nickel chrome moly steel. Okay? Plate steel. But only the Navy calls it actually not only the Navy, everybody else who uses it, but mostly the Navy uses HY80 or HY100. Okay? HSLA 80 is an outgrowth of ASTM A710, as I remember. Okay, so ASTM has got tens of thousands of specifications, and you can buy them for 40 bucks a piece, and ASTM makes lots of money. Okay, but it is a way for buyer and seller to come to an agreement. If on the purchase order I say A106 pipe, I know it's seamless. I know what the tolerances are on the thickness, on the how oval, you know, how round it is, how much ovality it can have. There's, you know, it's a 20-page specification that I just say A106 on the purchase order, and I get that extra 20 pages of the spec. Okay, that's how we buy steel, or copper, or aluminum, or plastic, you name it. Okay, so anyway, we have these hardenability curves. And so it's a function of thickness because the thicker it is, the slower it cools when you quench it. If you do a water quench of something that's 1/8 of an inch thick, it will cool very quickly, obviously. If you put a piece of steel that's 2 inches thick in water, it cools a lot slower. In fact, you generate lots of steam. Okay? It's a function of the alloy content. So HY80 is a thicker plate. Let's say you're going to use it anywhere from 1/2 inch to 4 inches thick. And there's an average thickness in a submarine, which I can't tell you because it's classified. Because if you knew that, you knew the diameter of the submarine, you could calculate how deep it could go. And in fact, if you go down to Quonset Point, when they're building the sections, which are just vertical tubes, okay, they do it indoors. And if they have it outdoors, they put a big tarp over it because the Soviets have satellites that can measure the wall thickness from space. And they want to know if it's 3 inches thick or 1/4 of an inch thick of the outer hull, because they now know the diving capability, which is classified. Which I know, but I'm not supposed to know, but I didn't get a security clearance to learn it. But anyway, but I can't tell you, but you probably already know anyway. Right? Approximately. So it is more than 1/2 inch thick, and it's less than 4 inches thick, but they do have foundations in there that are 4 inches thick. Okay? That's typically for about a 30-foot diameter submarine. Now a smaller submarine, I worked on a titanium submarine which was not classified. The purpose was classified, but Draper Lab was building it, and it was a 1/4 inch thick wall, and it was like, I think it was 4 foot diameter. Okay? And if you start figuring the strength of titanium and everything else, you could figure out how deep that thing could go. 4 inch diameter sub, 1/4 inch thick, go a lot deeper than 30-foot sub is however thick it is, right? Now, the problem with the alloying elements, so I don't say, well, why don't we use alloying elements all the time? Well, there's some good reasons you don't. First of all, alloying elements cost money. And typical prices of nickel and dollars per pound that you're going to use in the form of nickel that goes into a steel furnace, right now it's about $6.50 a pound. So dollars per ton at 1% concentration is $130. And I think HY80 is about 3.5% nickel. If I was talking HY80 or HY100, take your choice. So 3.5 times 130, by the nickel alloy alone, I just added $500 a ton to a product that probably starts out as a plate at about $1,000 a ton. That's for nickel. The chrome, which actually goes in, it goes in as an iron chrome alloy. It's only $1 a pound, and it's $20 a ton, and I think we got about 1% or something, okay? So you add a little bit there. Molybdenum, which is in HY80, as I remember, about 0.5%. It's $9 a pound, $180. So what's 3.5 times 3? It's about $450, $20. Moly might be in there at 0.5%, so we're talking $90. You start adding all this up, and you double the price of your steel. Okay? Now, it's not that big a deal in the quantities that the Navy buys for submarines, but if I'm General Motors and I'm making an automobile, $10 a ton when I'm buying 2 million tons of steel gets into real money. And so these people want the steel companies to control it very, very closely. Okay? Here's another one to pass around. We're going to go through in a second, I guess. So alloys cost money, but in addition, as they increase the hardenability, it makes it easier, particularly when you're welding, to get a high hardness in the heat affected zone. Because you're arc welding, you're melting this, you're going to have a heat affected zone. In general, when we get to hydrogen cracking, you're going to learn that anything above Rockwell C30 gets to be a pain to weld. And you have to do preheating and all kinds of other things that you've seen in shipyards. The thicker it is, the higher the alloy content, the more difficult it is to weld. Okay? I don't think I've told you the story of, I think it was Professor Ingram, who I think is retired, but this was back when we had a Course 13, which is Naval Ocean Engineering Program, Naval Architecture and Ocean Engineering. And he was working on one of the America's Cup yachts. In fact, this was the year that 2 MIT professors in Course 13 were designing the competing yachts for the America's Cup. Okay, so I had to lock their offices from each other, I guess. But anyway, this is also, I think, the year that David Koch of the Koch Institute, and David Koch got a degree from the Chemical Engineering Department. He and his brother inherited KOCH, okay, inherited a couple of billion from their father, and they've turned it into a couple of tens of billions, so they've got a fair amount of money. Anyway, so he wanted to do an America's Cup yacht, and this was like 10 or 12 years ago. And Professor, pretty sure it was Jerry Ingram, But anyway, he was designing the hulls and stuff for this yacht, and he's also a person who gets in early, so he calls me up at 6 a.m. Actually, this might have been 20 years ago, as I think back about it. And he asked me if I can come over because the keel beam, not the keel beam, but they have a keel beam, but coming down from the keel beam, you have this thing that sticks down to keep the sailboat from tipping over, right? It provides the resistance for the sail force. This is the water force in that beam that's being pushed by the wind up here, but you got to push back with the water here and stuff. What do you call that thing? It's a
keel or a centerboard.
Centerboard, yeah. Okay. So I don't know if in this design ship, okay, but anyway, it's a keel or a centerboard, but it's not the keel beam. Keel beam is the bottom beam that you build everything from. But anyway.
The mast, right? The mast runs all the way up
Yeah,
and down.
yeah. And this was like 4-inch thick HY80, and they were bending it. Okay, when they were doing the sea trials, it was bending, and that wasn't a good thing. Okay, so he said we want to use 4340 steel. So you asked about the 4 digits. Well, nickel, chrome, moly, vanadium. Okay, it's got vanadium along with nickel, chrome, moly, and I could give you the cost of vanadium. Actually, the cost of vanadium is about $10 a pound. Okay. And so that's $200, but you only put about 0.1% vanadium in. This is an HY80, but if you had 0.1% vanadium, you're only adding $20. But you can get your strength from a HY80, which was 80 KSI. They wanted to know if they could use HY180. I said, forget it. Okay, the Navy developed that. It's almost impossible to weld. Even the Navy doesn't use it. They just built a couple little prototypes and decided too difficult to weld. But 4340, they were all excited because you could heat treat it. You get 200 KSI. Yeah, you can get 200 KSI. You get cracks behind your weld too. How good is that? But anyway, they wanted to make this thing out of 4340 because they had to keep the weight down. They needed the strength, and so we developed a welding procedure for 4340, and that's what they finally ended up using. However, the preheat for 4340 is about 600 degrees Fahrenheit. Okay, how'd you like to be the welder next to a 4-inch thick piece of steel that's at 600 degrees Fahrenheit? You actually have to wear reflective clothing, and you have air pumped into your reflective clothing and stuff. In fact, when they redid the Seawolf in the early 90s, the problem with the Seawolf is they were using HY100, which is this composition. I wrote down HY100, same as HY80, just tempered at a lower temperature to retain a little more strength. But the weld metal was much higher, and it was on the high side. All the alloying elements were you have a range for each alloying element. The carbon might be between 0.08 and 0.16. Well, what did they have for the carbon? It was 0.15. Is at the high side. The chrome was supposed to be 0.2, and it was 0.19. It's supposed to be 0.2 to 0.3, and it was 0.29. This heat of steel that they made the welding wire out of for the first 18% of the vessel was on, we called a high side chemistry, and it was really more like an HY130. And they should have been doing HY130 welding procedures because the weld metal, was basically HY130, and that's why they got cracking. Okay, that and some other things which we can talk about later. But that's why you try to keep your alloy content down as low as possible to save money and to make welding easier. Now, one of the problems that we've always had up through the 1960s anyway in steels is you had to heat them up to make plate. You had to heat them up at 2200 degrees Fahrenheit to roll them. So the stuff is sort of yellow white hot, and it's going through the rolling mill. It doesn't melt steel rolls because you're going through there quickly, okay, and sometimes they're water cooled too. But the problem is the steel is so massive it cools down slowly. You get large grain size, okay, and large grain size gives you poor toughness. We talked about toughness yesterday. And so in the in the early 60s, some of the U.S. steel companies, not U.S. Steel, it was actually Inland Steel, started trying to make sheet steel for cars by cooling the steel, the hot rolled steel, with basically a water spray. I mean, just like a spray from your garden hose. They just put this in the steel mill and they could cool the steel down more quickly, they could get a finer grain size, and they could double the strength. And they called that a high strength, low alloy steel. It started out as sheet metal. They spent hundreds of millions of dollars building facilities to cool this stuff and temper it and everything. And they never could convince the automotive companies to buy it at that time. And what happens is the Japanese come along and they say, oh, we could make plate like this. And we could sell this. The Japanese sort of had a sweetheart deal between their steel companies and their shipyards. And they could do the research and provide steel for the shipyards that didn't have to be preheated. Saved a fortune, okay, in the shipyards. And so they started making high strength low alloy steel plate. And that was one of the reasons the Navy sent me to Japan in the mid 80s, because the Japanese had these high strength low alloy steel facilities where basically the hot plate after coming off the rolling mill would go into this tunnel. It was just a big spray booth of water. And you would quench it, or you would cool it at a very, no, you wouldn't quench it, but you cool it at a very controlled way. You wouldn't get martensite. You weren't trying to get martensite. You were trying to get very fine grain size. And you could get grains that are about 20 times smaller, which makes them about 8,000 times volumetrically smaller. Okay, you got a cube 20, right? Okay. So if at 20 times finer grain size, they could get fantastic toughness. Okay. They were low carbon, almost no low alloy. I mean, you didn't have to pay all this, but you were paying for it in the processing of having this steam tunnel to quench the stuff. Okay. And this was great. That was fantastic. But we didn't have it. And so the U.S. Navy wanted to learn more about this. They sent me over to the Office of Naval Research for a year, and I visited steel mills, and I'd walk by these big steam generators. I mean, just steam pouring out of these things as they're quenching the big plates with water. And we came back, there's something called Title III program, where the government can help a company invest in technology that has some significance to the government. And so turns out Lucan Steel got $100 million or whatever of Title III money, and they put in a high-strength alloy plate line. That was in the 90s, and that's where the HSLA steels that you use come from. Okay, it's no longer Lucan's. It's been bought out about 2 or 3 times because the steel companies are all going bankrupt. But the reason we have HSLA steel plate facility in the United States is because the Navy funded it, because they wanted better weldability. They wanted to be right up there where the Japanese were 20 years before. Okay, so we have to worry about the thickness and the alloy content, and of course, if you're surface ships, you're talking about 3/8 of an inch rather than inches thick. So now that one went around. Okay, so if we look at this one. Let's look at this one first, which is a very busy, I'll blow it up in a second, but you have a copy of it. Comes out of a book called Weldability of Steels by Bob Stout, who was, when I was at Bethlehem Steel in the 70s, he was Dean of Engineering at Lehigh University. And one of his compatriots in the 50s was a guy named John Gross. And Stout and Gross were 2 of the people who invented basically HY80. And John Gross ended up leaving Lehigh University in the 50s and eventually became Director of Research at U.S. Steel Research Labs. But anyway, this is the 4th edition. This is like 1980. Bob Stout's passed away now. But in the back of this, there are these tables that go on for about 40 pages that have about 200 different steels. Okay? And what I gave you is the first page of this. There's an index that goes with it. And so when someone calls me up, I used to get these calls a couple times a year when I worked with a particular company around here. that's a civil engineering company, and they would be, let's say this was the same company that was rebuilding the MTA station, and they're rebuilding something, and it was built in the 1920s, and they say, Tom, we got a piece of steel, we got to weld to it, and when we're doing this repair, what's the welding procedure? Okay, well, I go to Stout and I try to find one of these 200 steels that has, we don't have ASTM specs back in the 1920s for this particular steel. But I tell them I need to know the chemical composition of the steel. So they get some little drillings out of the piece and they send it off to the lab and they bring me the chemical composition. And I say I need to know the thickness. Okay? So I need to know the thickness and the alloy content. And I also get the carbon content from the alloy composition. Okay? So I have hardness and hardenability on that steel. And I try to match it up to one of these 200 steels that's in Stout and Doty, and Stout and Doty's table here gives me the welding procedure. Again, you know, being an expert is sometimes just knowing where to look, right? That's what I said before. So the first thing is the carbon range. That's your hardness. The next thing is the thickness, okay? This sort of fits together with what I just put up on the board, right? And the thickness range, they may break it up, because how fast it cools depends on how thick it is. You know, I'm putting the same size weld bead on, okay? Thicker, faster cooling. Minimum preheat or inner pass temperature in degrees Fahrenheit, depending on what type of electrode, whether I'm using low hydrogen or other than low hydrogen, which means high hydrogen. This particular steel, which is ASTM A27 steel castings, this is your garden variety, cheapest steel casting you can think of. Up to 0.25 carbon, so that's low carbon. These castings come in medium carbon too, and so you have to break this up and into low carbon and low medium carbon and medium carbon. And down here you can have some residual alloying elements, and you have to take into account those. And in fact, you're going to find that here, if it's nice low carbon and thin, relatively thin, I don't even have to preheat it. I just says I have to be above 10 degrees Fahrenheit. Okay, actually the ASME code says you have to be above 50 degrees Fahrenheit, which is actually much better because you get rid of all the moisture. 10 degrees Fahrenheit, I could have frost on there, right? Now I'd be burning the frost off as I weld along, but nonetheless, the ASME code says you cannot weld if your plate is less than 50 degrees Fahrenheit. But ambient, basically, if I come down here with alloy content, even with higher carbon, I got to have at least 100 degree preheat, and if I don't have low hydrogen, and if I'm very thick, it might be 400 degree preheat. When we redid the Seawolf, they were doing 400 degree preheat. And what they had, anybody ever hear about the blue jelly suits? Okay. Well, how'd you like to go into an egg crate that's preheated to 400 degrees? You're in an oven. And so they put the welders, they suited them up on little, so they had to roll in there on their backs on these little dollies like a mechanic's creeper, right? In an automobile, you know, working underneath the car. They put them in there, but they were suited in these blue jelly suits. And they were pumping this fluid, this cooling fluid. They were putting them in a little air conditioner, okay? And they had respirators because they couldn't breathe the 400 degree air for very long. It's not good for your lungs. So they're going in with sort of space suits and these blue jelly suits, and they could weld in there. I think they were allowed 15 minutes at a time. And you want to know why the Seawolf repaired cost $2 billion, okay? These are some of the reasons, okay? It was only a $500,000 hull, but it cost, anyway. I've been told that the final cost of the Navy was $2 billion because they had some high side weld chemistry. Then you look at, so you may have to preheat more if you're other than low hydrogen. Post-weld heat treatment, desirable at 1100 to 1200 degrees Fahrenheit to get rid of residual stresses. Is peening necessary? Well, you get thicker, you may have to peen to get rid of residual stresses, because it may crack before you finish the weld. Remember that great big thing, you know, the 17-inch weld I brought by? When you get very thick, it's going to take you, that thing took 2 days to weld up, okay, with 600 passes or whatever, and they were only doing short lengths. So you may have to stress relieve as you go, which means you go in there and pound it with a hammer every now and then. And I'm pretty sure it was, this may be before any of you were born, but back, I think it was in the 80s, the USS Iowa battleship was down in Puerto Rico. Anybody know this story? No one knows the story. So apparently they had a couple of gay sailors, and one of them had been jilted by the other. So he decides to blow up the turret that his former, I guess we call him partner, is in. And so he does. And it blows up the turret on the Iowa down in Puerto Rico, and just set off one of the 16-inch shell bags or a couple of them. But anyway, the U.S. Navy didn't know how to repair it. Okay, the Iowa, let's see, which one did they sign the treaty with Japan on? Missouri. That was the newest that was afloat at the time, but I think the Iowa or the Wisconsin were in the shipyard being built. They hadn't been completed, okay? But at the end of World War II, they had a couple of battleships that weren't. Anyway, the Iowa or the Wisconsin, I think, were the last two in service. And they finally took them out of service in the 1990s or something. But the shells and the powder had all been made during World War II. And you know, back in the 1980s, one of the Israeli conflicts, they actually had a battleship lobbing shells from 15 miles offshore into some of the. Anyway, that's the last time they actually fired shells in 16-inch shells in.
Gulf War they had.
Pardon me?
I think during the first Gulf War they had.
Oh, did they?
Battleships and so on.
Okay. Did they lob shells?
Yeah.
Did they? Okay. Well, they're big shells, and they go for about 16-mile range or something. So now you got a jet that can go for 200 miles away, right? Anyway, so it turns out the Navy didn't know how to repair. They had lost the technology of the different type of peening you would have to do to weld something that's 14 inches thick. So they decided just not to repair it. Okay, well, you got a couple of other turrets there, and how many ships